Actuary dude here, looking at another exam question. So it says, an actuary, it's always an actuary, is using a simulation technique to estimate the probability theta that a claim on an insurance policy exceeds a given amount. And it's carried around already 50 simulations and it's produced an estimate, and it thinks that theta is approximately 0.47. So the variance of the simulated values is 0.15. So it wants us to find the minimum number of simulations that will have to be performed in order to get theta within 0.01, and we're going to be 95% confident about that. Okay, so we're going to use what they show as being the absolute error method. And so the way we're going to do that is we're going to be saying that well, firstly, we can say that theta, what it actually is, minus theta, what we've estimated it to be, is approximately normally distributed with a mean of 0, and it's got a variance of tau squared over n, where we're going to say tau squared can be estimated because that's the variance here, the variance of the simulated values being 0.15. Okay, and that's squared. So we know that bit, and so we can then say that the probability, and because it's normally distributed to 95%, so actually I'll just put down that alpha being 0.05. So on the negative side, the negative z-score of alpha on 2, so going to just the 2.5% side, that's negative 1.96, and you can find that in the tables, which is less than or equal to. And we've got down our x minus our estimated x, essentially, when finding a z-score over there, and that's going to be divided by the square root of the variance of this bit, which is tau squared over n, and n is what we want to find. N is the most important bit in this whole question, which is less than or equal to, and again we have z alpha on 2, and that's 1.96, and that's going to equal a probability of 1 minus alpha, which happens to be 0.95. Alright, and because normal distribution is symmetric, we can do this on either side. We've got the same figures. When we're going to be dividing by a negative number, the signs will flip, so it doesn't matter too much. Let's just pick one and just go like this. And another important thing to say is that in the question, it's saying that it wants the difference between what we've estimated and what we're expecting to be no more than 0.01, because it says it wants to be within 0.01. Okay, so let's use that, and so let's just say here that we're going to have theta minus our expected theta, which equals 0.01, divided by the square root tau squared on n is less than or equal to 1.96. So let's just sub in some numbers that we know, and we're going to say that 0.01 is going to be less than or equal to 1.96 times by the square root tau squared is going to be 0.15, as we already established, divided by n, the only number we need to find over here. So we have 0.01 divided by 1.96, bring it to the other side. We can square the whole thing to get rid of that square root, and that's going to be less than or equal to 0.15 over n. So then we can just say that's the equivalent of n is greater than or equal to 0.15 divided by that whole 0.01 divided by 1.96 all squared. And now we can find out what what the minimum number that we need. So what was that? That was equal to 0.15 divided by 0.01 divided by 0.196, and that bit squared gives us 5,762.4. So we know n is greater than or equal to 5,762.4. And we can't do 0.4 over simulation, so we'll just say that n is equal to 5,763. And that's it, that's the answer, that's the minimum number of simulations required. So ask if there's any questions, and thanks a lot for watching.